Hello friends, in Maths we will start chapter 5, continuity and differentiability. So the first we will discuss about continuity of the function. So what is continuity of function? So if any function is given, we draw the graph. For example, fx equals to given x plus 5. Just a general example we take. Then we draw the graph it. Then we know that f is defined for every real numbers, and so x0, then here we will get 0, 5. If we get 1 here, then x1, then 1, 6, minus 1, and minus 1, 4. And so like this when we draw the graph, then without lifting the pen we can draw the graph. Also we have studied the sine function graph, cosec function graph, sin and cosec function graph. Sin x function graph is starting from 0, pi by 2, pi, 3 pi by 2, 2 pi, then 5 pi by 2, and so like this so it goes. And it continues. So we have seen this graph of sine, cosec, and that. In that we do not require the lifting of pen, and so such functions are called continuous function. But if we take some function like fx equals to 1, when x is less than or equals to 0, and fx equals to 2, when x is greater than 0, then we construct this graph, then we get like this way. Fx equals to 1 and x less than or equals to 0. For negative number it is 1. So like this way we get, and it 2. So here we say that here we can continue draw, but for when we comes to 0, then we positive numbers we go, then here we have to leave the pencil, and so such function is discontinuous function. And so we can say that if f is a given function which is defined, or f is defined on every point of its domain, means one real number, and or f is, or you can write f is a real function then we can write limit x tends to c, fx equals to fc occurs, means at every point of its domain the fx equals to limit we find out is equals to the value of its c, then we can say that f is the continuous function. So now we know that limit is defined when left hand side value and right hand side limits are equal, means limit x tends to c minus fx means left limit, and limit x tends to c plus fx means the right limit is equals to fc occurs. Then we can say that the f is the continuous function. So let's see some example here. Example number 1 is given. Check the continuity of fx equals to 2x plus 3 if x equals equals to 1. So we need to check the continuity of fx equals to 2x plus 3. So we can see that f is very well defined in x equals to 1. So we can write f is defined in x equals to 1, and so f1 equals to 2 into 1 plus 3, that is 5. Now f is defined at x equals to 1, so at x equals to 1 find out the f limit. Then limit x tends to 1, fx equals to limit x tends to 1, 2x plus 3, which is again 2 into 1 plus 3 equals to 5. So we can write that limit x tends to 1, fx equals to f1, and so f is continuous if x equals to 1. Now we have the example number 2, that examine the continuity of fx equals to x square if x equals to 0. And so we know that f is defined if x equals to 0, because x square value is existing, and so f is defined at x equals to 0, so f0 we calculate, that is the 0 square will be 0, and limit x tends to 0, fx we calculate, at x equals to 0 we calculate the limit, then it is limit x tends to 0, x square, which will be 0, and so we can say that limit x tends to 0, fx equals to f0, and so f is continuous if x equals to 0. Now we have the example 3, discuss the continuity of fx equals to modulus x if x equals to 0. So we know that modulus function is defined at x equals to 0. So we will write that f is defined at x equals to 0, and as it is defined at x equals to 0, we can write that fx equals to modulus, f0 equals to modulus 0, that will be 0. Now we will find out limit at x equals to 0, and then x tends to 0 of fx, then it is limit at x tends to 0 modulus x, and that will be 0, and so we can say that limit x tends to 0, fx equals to f0, and so f is continuous if x equals to 0. Now example 4, we have discussed the continuity of f given by fx equals to x square plus 3 when x is not equals to 0, and 1 when x is equals to 0. So here clearly it is given that f is defined at every point x belongs to R for all x belongs to R, and so f0 we take, then it is 1 given, and limit x tends to 0, fx we take, then now it is x tends to 0, it is not a 0, and so we write limit x tends to 0, x square plus 3. So x value we submit as 0, and it goes towards the 0, so 0 plus 3, then it is 3, and so here we can say that limit x tends to 0, fx is not is equals to f0, and it is not equal to f0, and so we can say that f is discontinuous at x equals to 0. We have the example 5. Check the continuity of fx equals to k, means the constant function. For x belongs to R. So now x is belongs to R, so we know that constant function is defined in every real number, and so we can see that for every x belongs to R, f is defined, and so if c belongs to R, then fc equals to k. Now we find out limit of that. So limit x tends to c, fx equals to limit x tends to c, that is k, and it is k, and so we can write that limit x tends to c, fx equals to fc. So f is continuous at for every point of x belongs to R. Now example 6, we have proved that the identity function is continuous function. So we know that fx equals to x is where x belongs to R is identity function. And so we know that identity function is defined at every point, and so f is defined for all x belongs to R, and so we can write that if c belongs to R, then fc equals to c, and so here we can write that limit x tends to c, fx equals to limit x tends to c, x, because fx equals to x, which will be c, and so limit x tends to c, fx equals to, it becomes fc, and so we can say that f is continuous in every x belongs to R. Now we have the example 7. Is fx equals to modulus x is continuous function. So already we have seen in the previous example that f is continuous if x equals to 0. Now we know that fx equals to minus x when x is less than 0, and x when x is greater than 0. So we take the left limit x tends to 0 for c belongs to R. There are two conditions. If c less than 0, then fc equals to minus c, and c greater than 0, then fc equals to c. And so here we can take for c less than 0, limit x tends to c, fx equals to limit x tends to c minus x, which will be minus c, and for c greater than 0, limit x tends to c, fx equals to limit x tends to c, x, which is c. And so in each case it is limit x tends to c, fx equals to fc efforts, and so we can say that f is continuous at every point of x belongs to R. So we know that f is defined at every point c belongs to R as it is the polynomial function, and so fc equals to, we can write c cube plus c square minus 1. Now limit x tends to c, fx we write that will be limit x tends to c x cube plus x square minus 1. And so it will be c cube plus c square minus 1, which is equals to fc. And so here we can say that f is continuous if every x belongs to R. Now here example 9 we have discussed the continuity of fx equals to 1 by x where x is not equals to 0. So here x is not equals to 0 is given, that for other values of x except 0 fx is value and we know that. And so we can write that f is defined for every x belongs to R where x is not equals to 0. And f is defined, and so if c belongs to R we take, then fc equals to 1 upon c, and limit x tends to c, fc we find out, and it is limit x, fx we find out, and limit x tends to c 1 by x, which will be 1 by c, and so we can write that limit x tends to c, fx equals to fc, and so f is continuous for every x belongs to R except x is not equals to 0. Now to example 10 we have discuss the continuity of fx equals to x plus 2 when x less than or equals to 1 and x minus 2 when x greater than or equals to 1. So here we can see clearly f is defined for every point of x belongs to R. So now for any c point, so x is c equals to 1 we take, then f equals to 1, f1 will be 1 plus 2 equals to 3, and limit x tends to 1 minus left limit of 1, so less than 1 fx, we write then it is limit x tends to 1 minus, so smaller than 1, then we have here function x plus 2, this is 1 plus 2 equals to 3, and limit x tends to 1 plus means right limit we take, and limit x tends to 1 plus, for the right limit means greater than 1, it is here x minus 2, and so 1 minus 2 which will be minus 1, so we can see that its limit, left limit and right limits are not equal. In x equals to 1, in x equals to 1, right limit and left limit are not equal, so we can write that f is discontinuous if x equals to 1.